Today I'm very pleased to present Steve Cox, Head of Future Networks. Steve, please begin your call.
Good morning everybody, and thank you for joining our first webinar on the CLASS project. So in terms of the agenda for the presentation, I'm going to overview the low carbon challenge, certainly as we perceive it at Electricity North West, just introduce the company for those of you who are not familiar with us, and then look at the general background of the UK energy and carbon challenge. We'll then turn to a little more detail on the CLASS project itself, and also what the project contains and the role of our partners and what we intend to deliver at the end of the project. And then finally we'll finish on the question and answer session. Okay. So first of all, Electricity North West. As the name suggests, we serve the northwest of England. We're a pure play DNO company. We don't have any supply business or any generation assets. We serve around 5 million customers, 5 million people in the northwest of England, about 2.4 million customers, and we operate over £9 billion worth of assets. And the company in the exploded diagram is really a microcosm of the UK. In the south of the company, we have the very dense urban conurbations of the city of Manchester, which is one of the highest demands outside of London. In the central belt of the company, we have the industrialised area of Lancashire, and then in the north of the company, we have the Lake District National Park area, which is an extremely rural network and exposed to some quite severe weather, particularly in the mountainous areas. So our network also, because of its long western seaboard, is very attractive for wind turbine generators, and we've seen a large amount of DG developing our network over the past few years. In fact, we've now passed the 50% mark in that we have 2.5 gigawatts of DG connected to our network and a total demand of around 4.8 gigawatts. If we look at the context of the challenge facing the UK in terms of its carbon emissions, we're in a position at the moment where predominantly the energy economy is based around gas and oil and coal. And the graph that I've put up at the right-hand side of the slide shows the government's CO2 emission targets. Now, the blue line represents the carbon intensity of electricity generation, and the red line represents the effectively carbon intensity of energy consumed by customers. And the little yellow area represents our Rio ED1 business planning period from 2015 out till 2023. And there are a couple of things I'd like to just pick out of that graph. First of all is that you'll see that the challenge facing us in ED1, and particularly in the northwest, is much more acute for facilitating low carbon generation being connected to the network. We will see a transfer of transport demand and heat demand away from gas and coal onto electricity, but the change in generation mix, particularly affecting DNO networks, is much more marked during this period. So I guess the question is, so what? Well, if we met that challenge for demand and generation through traditional means, then that would mean, quite significant price increases for customers. And given the current economic climate and the pressures on businesses and households, that is just not acceptable, and therefore the challenge for all network operators, including Electricity North West, is how can we facilitate that change at a lower cost for customers. Now, part of that, in meeting that challenge, is our research and development programme, both within Electricity North West and within the UK network operators more widely. And at the moment we have around £30 million worth of in-flight R&D projects, 60 separate projects, and this morning we're going to look at one of those projects. In terms of trying to articulate the scale of the challenge, if we just look at the little chart at the top right-hand corner of the slide, up the left-hand side we have the amount of electricity used by a typical domestic household, and along the bottom axis we have the time of day, and this is the electricity consumption for my house. So you'd see, this typically for most houses in the UK, small amounts of power being used by some intensive appliances such as washing machines, but only for a relatively short period. And the chart below it predicts what the demand would be at my house and the usage pattern would be if I bought a heat pump to replace my gas central heating system, and if I bought an electric vehicle to replace my diesel car. And you see a huge contrast in the two consumption patterns, both in the amount of electricity used, the peak demand being much higher at over 14 kilowatts, particularly in cold weather, and also the duration of usage of electrical energy at that property. And that is a significant challenge for network operators such as ourselves in how we operate our networks to manage that change. The table on the left-hand side of the slide shows some typical figures for our network and the consequences as we move out to 2035. And the one figure that I would pick out is probably Manchester in terms of the transport. Manchester has around 220,000 cars commute into Manchester every morning. And if we went forward to a future where those cars were electric vehicles and sought to recharge when they reach their work car parks, then that would add around 400 megawatts to Manchester's demand. Now, Manchester's current demand is only just slightly over 400 megawatts, so within the city we would see a requirement to double capacity if we didn't do something more smarter to resolve some of those reinforcement issues. Our strategy at Electricity North West really is focused around, first of all, maximising the use of our existing assets. As I said before, at the beginning of the presentation, customers have already paid for in the region of £9 billion worth of electricity distribution assets, and therefore, as well as looking at new technologies such as energy storage, we also are very focused on how we can maximise value generated for customers from those assets. Our innovation strategy is really about trying to provide solutions using existing assets to problems that customers have today and will have during the RIIO-ED1 period, and then in the medium term looking out to ED2 and ED3. But very much the focus of our two Tier 2 projects is about maximising value for customers during the RIIO-ED1 period. We've been successful in achieving funding of over £20 million under the Tier 2 of the Low Carbon Networks Fund, and we are currently running two projects, the CLASS project, which we're going to look at this morning, and our Capacity to Customers project, which we've run a number of learning and dissemination events on. But I'll go on now to look at CLASS in a little bit more detail. Okay, so as way of introduction, we're going to show a video that introduces some of the principles behind CLASS. And essentially, CLASS is all about using network voltage in new ways to change the electricity demand on the network at different periods, and also to change the way we use primary transformers, in other words, tap-changing transformers that exist already in the network, and to use those in a way that maintains the service that customers have always enjoyed, but delivers new services to them and contributes to the low-carbon economy. we just go back to school for a moment. I think what we're trying to look at with class really is the relationship between the voltage at a customer's premise and the amount of electricity consumed by the appliances. In other words, the demand, the real-time consumption rate of electricity. And essentially, underlying that relationship is the principle that if you increase the voltage, then demand will increase, and vice versa. If you decrease the voltage, demand will decrease. And within class, we're seeking to explore that relationship, and particularly how it will change over time as customers change their appliances from the ones that are probably in the homes at the moment, from things like tumble dryers, and move on to heat pumps, and particularly things like electric vehicle recharging. So how does it work? So we take a very simple example just to illustrate the principle. It takes about 3 minutes to boil a full kettle in your home. So if we increase the voltage to your house by around 2%, then the kettle will boil around 8 seconds faster. And similarly, if we reduce the voltage to your house, it would take you about 8 seconds longer to boil the kettle. Now, critically, the amount of electricity, in other words, the cost to boil the kettle, would be the same. And we're seeking to test within the project whether customers would actually notice that tiny change in the consumption pattern of their appliance. Would you notice 8 seconds in a 3-minute boil cycle? Similarly, if you were cooking your tea with an electric oven, would you notice 1 or 2 minutes on your cook time? The second principle of class is to coordinate the changes in appliance behaviour across large numbers of customers. In other words, to aggregate the response provided by domestic appliances. And there's an old adage that says, a problem shared is a problem halved. So if you can imagine combining the response of all the appliances in 20,000 homes in a town, or 200,000 homes in a city, or 26 million homes in the UK, if you could make all those changes happen at just the right time and in just the right direction, what problems could we solve with that type of demand-side response? So this principle of millions of indiscernible changes in appliance behaviour and combining them can have a huge and potentially valuable effect for the UK. So first of all, we look at problems today. So typically, a DNO will face a problem that as demand increases in an area, then it eventually exceeds the network capacity, and the network operator needs to reinforce the network. So if we were able, at time of peak demand, to just turn down the rate of consumption, in other words, the demand for electricity, just by 1 or 2%, then that can help not only defer reinforcement and in some cases prevent it, but also allow more low-carbon technologies such as heat pumps and EVs to connect to the network more rapidly. Also, if we operate the tap changes in a mode that's called tap stagger, which is we operate the transformers at our substations on different taps, we can use that to absorb large amounts of reactive power from the transmission system. And that's a very real problem that the transmission operator, National Grid, face today, and it's a problem that network operators such as ourselves will increasingly face as more and more DG connects to our network. Looking forward, looking further to response and reserve, as you saw on the little video clip, the current way of compensating for the loss of a large power station in the UK is to carry effectively a number of spare power stations spinning on the system, known as spinning reserve, and those power stations emit carbon, and they cost a lot of money, around £250 million a year in the UK, to provide that spinning reserve service. What CLASS seeks to do is to provide that emergency frequency response from the demand side rather than from the generation side of the equation. In other words, balance the scales by these millions of tiny changes in demand. And if we can do that quickly enough, and we can do it at just the right time, then that saving can be passed through to customers and help keep overall bills down. As we look further into the future and the amount of particular wind generation increases in the UK, there are times, and we see this in other countries such as Ireland, where there is more wind energy available on the system than we can actually allow to be taken. And therefore that wind is spilled, in other words, it's thrown away because we can't take that generation. And that has an effect of increasing the average price of energy. So if we apply a slight voltage increase to customers' premises, then we can actually increase the rate at which they consume energy and therefore keep more wind generation on the system at any one point in time and hence lower energy costs. So on this slide I'm going to look at the first of those scenarios, in other words controlling peak demand. And if we look at top left hand graph called scenario A, what I'm trying to illustrate here with the red line is the demand in a particular town increasing over time, and at some point it reaches the limit of the existing network capacity. And what the DNO would normally do is increase the amount of capacity to a new limit, and then the demand would carry on increasing. And that trajectory we've seen for many years in the UK, in other words, a steady background growth in load and DNOs intervening when necessary to make more capacity available to customers. However, over recent years, particularly with the growth of DG and particularly with the price of raw fuel and the drive for energy efficiency through new standards on appliances, we've seen a change in demand patterns, and some of our load groups are no longer following scenario A and they're behaving as per scenario B or scenario C. So if we look at scenario B, and central Manchester is actually an example of that, we've seen demand go through the existing capacity limit but then curtail and drop back down again. And that's not necessarily just driven by general economic activity, because Manchester is actually very buoyant economically. It's driven by customers installing CHP, by growth in solar generation, by more efficient air conditioning appliances and appliances generally. And that creates a problem in that if the DNO invests when the existing capacity limit is reached, then if the demand then falls away, those assets are a sunk cost and effectively need to be paid for by customers over the next 20 to 40 years, but they're actually adding no value because the demand's fallen away again. So the ability to curtail peak demand for a period and effectively buy optionality, in other words, buy time before committing very large capital investments, can really help, particularly in ED1, keep bills down for customers. At the far right-hand side, we see some other groups, and our Wigan BSP group is an example of that, where the demand oscillates close to or slightly above the existing capacity limit. And again, we intend to use class to control the demand, the peak demand in that group, to keep it within capacity limits so that we don't need to invest. And the key thing, I think, under the class project, when we show how the technology works and how it can be applied, is that can be applied at every substation in the network and has an enduring benefit. And we certainly believe in our load modelling that the scenario A will probably not be typical of the future, and we'll see more of the electricity network behaving as B and C as customers change the use, install generation, as DNOs buy DSR, and we have a much more active market and therefore a much more volatile demand. With slide 14, I'm trying to explain really how we intend to provide primary and secondary frequency response within the class project. So looking at the little wiggly line at the top left-hand corner, system frequency goes along fairly steadily at around 50 Hz. But if we lose a large power station or we lose the cross-channel link to France, then system frequency falls very quickly. And as we outlined in the video, if it falls too far, then bad things can happen, and we need to manage the electricity network in real time so that doesn't occur. So currently that's done by large standby generators, and what we intend to do using class is provide very fast sub 1 second frequency response using primary transformers. And we'll show probably at a more technical seminar in the future exactly how we intend to do that. But the initial work we've done shows that we can provide a very substantial and extremely fast and extremely configurable response in the half a second to 1.5 second period. And that is important because as more wind generation penetrates the system and displaces traditional coal systems, and as more photovoltaic comes on, the need for that very fast and very configurable primary response will increase in future. And the UK currently has an ancillary services market, which is where the £250 million is traded, and that's forecast to go certainly well above 250 million per year, and perhaps high as 500 million per year as more and more wind comes onto the system. After we've provided the very fast response, the primary response, which has an endurance of around 30 seconds, we then need to provide secondary response, which lasts up to a maximum of around 30 minutes. And that will again be provided by operating primary transformers in a different mode to how we currently operate them. Now, the key thing is this project is all about fitting intelligent control gear to existing main power system assets. It's not about putting large high capital value assets onto the system. So in the primary substations, which is where we regulate the voltage from 33 kV down to 11,000 volts, we will install new smart voltage control relays, which will be linked in real time to our control centre in Manchester. And they are really the brains of the system that allow us to adjust voltage on the network by very small increments whenever required, and to do it in a coordinated manner to provide the services, either voltage boost, voltage decrease, or frequency response that I've talked about before. Importantly, the changes are very small, and we never exceed statutory limits on the changes that we make. We're working with Siemens, our technology provider for the substation equipment, and those will be going into substations over the next 12 months or so. In the centre, in our network management systems, we are building dashboards in conjunction with GE in their power on fusion system. Now, the dashboard is a very important component of the CLASS project because that allows the control centres, both in the distribution network operator and in the National Grid Control Centre in Wokingham, to see how much response is available on the system from the demand side at any point in time, and also whether transformers are operating in demand boost or demand reduction mode. So that provides the coordination and the control that really unlocks the value from the proposal. We're also working with University of Manchester, who are providing a lot of the analysis of the relationship between adjustments in voltage to adjustments in demand. This, so far, apologies to some of the audience, is a very technology or engineering-led discussion. But really, CLASS hinges, or the acceptability of CLASS hinges on customers either not noticing or not caring about these tiny changes. And we're confident that customers won't notice these changes in voltage because of two reasons. First of all, they experience these changes every day as part of normal voltage regulation activity on our network. Typically, the voltage will change by 1 or 2% around 15 to 20 times a day for every customer in the UK. So by introducing a very small number of additional changes at times such as peak demand or for loss of a large generator, it's actually a very small number of additional changes in voltage, so we're confident they won't. However, unlike other demand-side response projects, this is not an opt-in arrangement for customers, so they don't agree in a consensual manner to partake in this kind of response. And therefore, quite rightly, the expert panel and Ofgem have set a very high bar in requiring us to absolutely prove that customers either don't notice or find the proposal acceptable. So CLASS contains quite a large piece of work on customer engagement to explain what we're doing to customers, to engage with both customers and stakeholders around their views, and to conduct a wide range of surveys to actually measure in quantity terms the effects as perceived by customers. Okay, in terms of the timescale for the project, we received funding in January 2013 and the project mobilised. We've completed our site selection and we're now commissioning and installing the equipment in substations, and that's really, that technology build phase is going to take us until the end of this current financial year. We then commence live trials, and we also commence our customer survey work. And as that progresses over time, we will start to publish our modelling reports, publish our findings into effects on asset health, and also start to show the learning on the carbon benefits of the work. Now, I mentioned the involvement of National Grid before, and National Grid are a major partner in the project. So as part of their contribution and our work together, we will also look at the recommended changes or potential changes that could be made to SQSS and some of the codes around system frequency control. That will take us probably until late summer 2015, and then as we move towards the end of September, we will close the project down. Now, what we will have as a legacy from the project is a long-term monitoring study which runs for 10 years beyond September 2015 that actually tracks the relationship between voltage and demand across a large number of our substations, around 60 of our main substations, covering nearly 400,000 customers. And that will show us, as customers' appliances change and we move from perhaps old type resistive loads onto more linear loads, how the relationship between voltage and demand changes over time. I've mentioned a few of our project partners. In the technical area, we're working with Siemens in the substations, Parkinson's Brinkerhoff in network selection and some of the analysis, National Grid in building the dashboards and understanding the relationship between voltage and demand, and GE are providing the technology in the control centres. University of Manchester will be involved in the long-term trial in understanding the relationships between the changes in voltage and changes in demand, and we're working with Tyndall Centre to understand the carbon effects. Chiltern Power are providing us consultancy across the project, and Impact Research are leading on the customer engagement activity. So all of our partners will be popping up at some time during the learning and dissemination events, and we're delighted to be working with them all. They're extremely experienced and have a wealth of experience in these project areas. Okay, our project team, I think probably apart from the bloke at the top, Craig McNichol is runs our Future Networks delivery program. Herb Costello is the project manager. Paul Turner is leading the substation and computer technology areas, and Kate Quigley is leading the customer engagement work within the project. So you should start to see all of these faces popping up at the learning and dissemination events. Okay, so just to sum up before we move to question and answer, we think CLAS is one of the first applications of real-time dynamic voltage control to generate new services for network operators and for system operators, and we believe it is innovative in how it brings those services to market. It does tap into world-class technology provided in the substation end and in the control centre end by Siemens and GE, and it has the potential, providing we're able to get all the technology to work and also get the customer engagement right, to provide real material financial savings for customers, but more importantly carbon savings to contribute towards the UK's carbon agenda. And a key output for me is that long-term understanding of this fundamental relationship. So I think at this point that's the end of the formal presentation, and if I pass over to the operator, if you press 01 on your telephone, that should allow you to register a question.
Thank you. While we wait for questions, I noticed there was a question already from Andrew Urquhart of SSC, and his question is, how would you ensure that customers at the end of a long circuit will still experience voltage within limits?
Yeah, really good question. As part of the network measuring phase of the project, we will measure the voltage at the end of feeders in the selected area, both on the high voltage network and on the low voltage network underlying. So one of the key learning points is how much demand reduction or demand boost can you obtain, and one of the elements that may curtail total volume available is the effect on feeder end voltage, the tapering effect on networks. So that's part of the study, and we will explicitly measure it. I think we also, on the customer side of it, for the technical side, there is a statutory limit, yes, but there's also a key element for customers. Do they actually notice that change in feeder end voltage?
Okay, in fact, Andrew's in the audio queue as well, so I'll just open up his line. Andrew, do you have any follow-up questions?
Yeah, it's actually on a separate topic there. I'm just wondering, as part, you mentioned that you were going to tie in with National Grid. Are you intending to operate commercially in the ancillary services market?
No, within the project lifetime, we will not bid into the ancillary services market in a commercial way. Effectively, the substation relays for a frequency event will automatically adjust demand down, but we're only doing that on a small section of our network, so we won't even do it on all 60 of our main substations. It'll be a small subset of that. So the amount of real demand response we provide within the trial will be indicative of what would be provided if it was rolled out across a larger number of substations, but it won't be sufficiently material to warrant adjustment of the current market commercial mechanisms.
Okay, so it's a proof of concept, and I presume you'll be sharing at the end that sort of how you get into that market, how you enabled it, and how it could work for a future operator.
Absolutely, yes. I mean, I think it's important to note the LTNF fund is paid for by distribution customers, and Ofgem were quite rightly keen to say the frequency balancing services market has its own incentives on NTSO, National Grid, to procure efficient services in the ancillary services area, and therefore we will not explore the full extent of the commercial scale and form of class. What we will do is carry out effectively quantification and an examination of technical elements and show how it could perform technically. I would probably see either a follow-on project, either within LTNF or perhaps outside LTNF, looking at the commercial viability of that service.
Okay, and indeed who'd be able to provide it, because that's probably not DNOs, but okay.
Yeah, there are a whole host of questions, such as, for example, would the DNO be able to actually bid it in as a commercial service, because the response is actually being provided by customers, and therefore, should it be a grid code requirement on DNOs to provide these balancing services, or would it operate in a commercial market? They're questions for the future. I mean, I think the first thing to do with class is to actually prove that technically you can do it, and you can harness these millions of responses in an organised and controllable manner to actually provide the response when required. Once we get past that hurdle, then we can start worrying about how much money we can make out of it.
Okay, thank you very much.
Our next question is from the line of Arun Pontin of Ofgem. Arun, please go ahead. Your line is now open.
Good morning, Steve. Aaron here. I was just wondering when you were going to begin your customer engagement campaign, because obviously that's going to be quite important to the success of the project.
Yeah, the customer engagement work, I think, is probably just worth expanding on for a few seconds. It's really in two parts. One is to establish a group of trial participants, and we can start to recruit participants fairly early on in the project, and to bring those participants up to speed in terms of their understanding of what we're trying to do, who Electricity North West are, what things like voltage mean to them. So I think there's a lot of upfront work. I think I mentioned that in terms of the project timescale, it was April 2015. Yeah. So I've just got one of my able assistants holding up some dates for me. So May 2014 will be the first time we actively engage with customers. Okay. But a lot of the survey design work will take place beforehand. I think one of the things we learned on our earlier project, Capacity to Customers, is it's actually quite hard to talk to stakeholders and customers about this type of technology, and there's a long learning curve, and you need to put a lot of work into preparing the right communication materials to help customers understand, and therefore they can give you an informed view of when you actually start customer engagement work. So we've actually commenced that preparatory work already.
Okay, great. Thank you.
Just to remind all participants that if you wish to ask a question, could you please press 01 on your phone keypad now, or type it into the Q&A box. And while waiting for any further questions, one has come through on the WebEx from Steve Mullins at Siemens. And his question for you, Steve, is what impact does the voltage charge have on distributed generation?
Well, I guess it's a good question, and I guess what we'll do is find out during the project. I think when we are dealing with networks, we are dealing with a collection of often hundreds of generators, or for domestic PV, potentially thousands of generators on a substation. And I think a lot of research has been done into the behaviour of individual machines, whether they be wind generators, CHP, synchronous units, or micro generation such as PV. But I guess there's an adage, studying one bird does not necessarily tell you how the flock behaves. And one of the key technical understanding areas we want to examine with the University of Manchester is exactly how DG behaves en masse when you make these changes to network voltage. So I guess it's a really good question. That's one of the things we're trying to find out in the project, and that will be covered by our learning and dissemination activities.
Okay, at this stage there seems to be no further questions, so may I please pass the call back to you for the polling and the close.
Okay, thank you everybody. Perhaps just remind everybody, by all means submit any questions online at the moment or to our email inbox, futurenetworks@tnwl.co.uk. There's also the details up in terms of our contact numbers, and any of our team will be happy to get back to you on any questions that you think of in the future. There'll also be regular updates on our website as we go through the project about not only the work we're undertaking, but also findings as they come up, and we'll also run a number of future dissemination events for you. So I think unless there are any final questions, just like to thank everybody for the time this morning. And as a final reminder, if you could just complete the poll questions that you should see on your screen, just let us know what you thought of the webinar and how we can make it better in future. Thank you very much for your time.